Well, in this section, I want to talk about the formation of the solar system, and I want to get into some details so that when I'm done, you'll walk away with an understanding of how our solar system came to be. And it's not a simple kind of idea. It's going to take a little bit of background. The first thing I want to talk about are these things called molecular clouds. Another term might be solar nebula. They're believed to be these areas of the sky filled with gases such as hydrogen and helium and even other things. Now, you know that during the Big Bang we had only hydrogen and helium created, so if these molecular clouds have other elements in them, which they do, it turns out, those had to come from the injection by a supernovae. So the supernovae are going to be very important in the formation of these molecular clouds, because remember, we believe the sun came from the collapse of one of these molecular clouds. And so it's got to have the right kind of composition before it collapses, or we can't get an Earth-like planet formed from it. Well, this picture is a picture of Orion. Orion is so characteristic, I can hardly believe that if you've ever looked up at the sky, you haven't recognized it. It's got these four characteristic stars around it, and then in the center it has three stars at a slight angle. That's referred to as Orion's belt. So I hope I'm hitting some memories here. If you haven't seen Orion, you need to go out and try to find it in the sky. It's spectacular. And if you look into the area of the belt, we can blow that area up here, and you can start to see some huge molecular clouds. Everywhere practically out there are molecular clouds, but in particular, look at the Horsehead Nebula and the Orion Nebula. These are very, very pronounced molecular clouds. I know this is hard to imagine, but the particles in that molecular cloud are moving at hundreds of kilometers per second. So I'm imagining that, your first question has got to be, well, why can't we see that moving? And the answer is actually quite simple, and that is that it's so far away that we couldn't possibly see it moving unless we stood there for thousands of years practically, depending of course on how far away it is. In this particular case, the Orion Nebula happens to be 1,344 light years away. And so when you get that far away, that's going to take that long in years for light to get from Orion Nebula to us. So it's kind of like if you're looking at a ship on the horizon, if it's way, way out, just barely see it, it's hard to see it moving. Even if it's moving across the entire plane where the sky and the ocean come together, it's still difficult to see it moving. And of course, if it moved in close to you and it was closer to the beach, moving at the same speed, you'd be able to see it moving, unless it was moving very, very slowly. But you get my point. My point is that the farther away something is, the slower it seems to be moving. These things are so far away that we don't even see them moving, and we don't get the perception of them moving. Now, I'd like to show you this video, and it's a molecular cloud it's a computer model of a molecular cloud collapsing, and it's forming stars. And the yellow areas that you see in the computer model are the actual stars that are forming. So you can see then that these molecular clouds are just like baby nurseries, breeding grounds for new stars. And here's another place, the Eagle Nebula, and it has two very interesting areas, and let me show you those two areas. They're the pillars structures here. These pillars were formed by incredible stellar winds that blew these pillars up, and we're going to focus in now on those two areas. And these are actually some fairly famous pictures. It was taken by Hubble Space Telescope, and at the tips of each one of these pillars, you'll see these little tentacles coming out, and each one of those tentacles, at the very tip of the tentacles, the small tentacles, there's a star that's being formed as we speak. And as soon as that star, completes this process, it's going to create a solar wind, and that wind is going to blow more of that molecular mass out. To give you an idea of just how powerful these stellar winds are, I want to blow up the area over on the left, the upper part of it, blow this concave area up so you can take a look at it. That concave area, which you saw on the previous slide, now is shown here, and that's due, we think, to huge stellar winds striking that and forcing it to collapse down. And of course, when it collapses, it forces the material in the clouds together, and gravity takes over, and that stuff then will collapse to form stars. And so these are the processes that we think went on to form our sun. I think one of the most interesting things, if you look in the Orion Nebula, is that we see these protoplanetary disks forming, and this is exactly what we would predict. Look at them. You can see them in the picture on the left, and then if you look down on the right, that's a blow-up of the dark disk there, and you're seeing in the middle, you're seeing a little star just beginning to flicker, and with all of the mass around it of that, what we call a protoplanetary disk. And this is important. We can model this, and if you have a gently rotating molecular cloud, and something forces it to collapse, like a supernova, and we'll talk more about that in a minute, and it collapses, it's going to collapse in such a way, gravity taking over, that it will, 99.9% of the material in that molecular cloud will go to the center and form a star in the center, in our case, the sun. The rest of it will fall into a disk that will be gently rotating around the center of where most of the material is. So the material that made up our planets, and I'll show you how the planets form in just a minute, that material that made up our planets is really a very small part of our solar system, as you probably remember from some early lectures. So all you need is a slight rotation of these molecular clouds and something to collapse it, and you get then these protoplanetary disks that we're seeing here. And we think that that's what our solar system formed from, a protoplanetary disk. All right, now let's call time out for a minute and go back to a very important point. What potentially collapsed, or what potentially forced a molecular cloud that formed our sun? What made it collapse? Well, that's a good question, and you might think, well, we have no way of knowing that, but actually we have some incredible evidence. I think this is one of the great discoveries of all time. It comes from, let's go back to those calcium aluminum inclusions that we talked about earlier when we were talking about meteorites. Those calcium aluminum inclusions, they are enriched in some important elements, isotopes in particular. And we see that they're enriched in isotopes that decayed from other radioactive isotopes that had very short half-lives. Let's talk about aluminum-26 as an example. Aluminum-26 decays to magnesium-26. You can see it up there in the left-hand corner. And it has a half-life of about 740,000 years. That's not very long when you're talking about a solar system that's 4.5 billion years old. So if you think about that half-life, well, that means that our aluminum-26 that was originally in our solar system was only going to be around for a maximum of about 7 to 10 million years before all of the aluminum-26 decays to magnesium-26. And then that tells us that in order to get aluminum-26 into a calcium-aluminum inclusion, that it must have formed in a supernova before that inclusion formed, incorporated in the calcium-aluminum inclusion, and then decayed to magnesium-26. I hope that's clear. So now look at what we're seeing here. We're seeing this beautiful correlation between magnesium-26, which is the product of a decay of aluminum-26 over there on the y-axis, and it's correlating with aluminum-27, which is a very stable isotope of aluminum. And what this is really telling us is that originally aluminum-27 was correlated with aluminum-26. That makes perfect sense. If you had a lot of aluminum in one calcium aluminum inclusion, then that aluminum 27 or 26 would have, or I should say if you had a lot of aluminum, you would have a lot of aluminum 27 and a little bit of aluminum 26. Aluminum 26 is not in as much abundance, obviously, as aluminum 27. And then that aluminum 26 decays away, leaving the aluminum 27 behind. It should correlate. If the aluminum 26 correlated with the magnesium 26, then the product of that magnesium 26 should correlate with the aluminum 27. It's a little tricky to think about, but that's how we get this correlation in the calcium aluminum inclusions. What does that tell us? Once again, let me repeat. It tells us that there had to be a supernova nearby our molecular cloud that injected our molecular cloud with isotopes like aluminum-26, and then it also probably forced that cloud to collapse. It had to do so pretty quickly. We only got 7 to 10 million years in order for those calcium aluminum inclusions to form with aluminum-26 in them, so that aluminum-26 could decay to magnesium-26. Now, a couple of cautionary things to tell you about, and that is that there wasn't just one supernova that made up all of the composition of our molecular cloud to get the terrestrial planets with the elements that we have today. Originally, we know that the molecular cloud was made up of hydrogen and helium. So that molecular cloud then originally had to be only hydrogen and helium. And then we've had these supernovas since the Big Bang that have been going off and injecting that molecular cloud with the requisite material that you need on a planet like Earth. And then there was one last supernova that went off that not only injected it with aluminum-26, but forced it to collapse. At least that's the way the thinking goes. And we get these nice correlations, so it almost has to be due to a supernova. Well, I shouldn't say has to, because then you start, getting into, okay, we don't want to be dogmatic in science, but it sure looks like a supernova was involved. And it's not just true for aluminum-26, it's true for other isotopes that decay rapidly. Iron-60, which goes to nickel-60, you can see there. Calcium-41, which decays to potassium-41. And beryllium-10, which decays rapidly to boron-10. So as you can see then, a lot of evidence for a supernova nearby our solar system. So that tells you then that why our molecular cloud that formed our solar system collapsed, and perhaps gives an idea of how it collapsed. And then we can surmise then that a protoplanetary disk formed from that process. Now, I want to go to this rather famous graph here. This is a graph of the density, and it's in grams per centimeter squared versus the radius, and this will be distance from the sun in AUs. One being, of course, an Earth distance, and you see the Earth plotted there with a density just under, well, it's 8 something, as I remember, and it's got all of the other planets there: Mars, Earth, Venus, and Mercury. And what was done here by Hayashi in 1981 was he had this clever idea to take the planets and spread the material that's in the planets evenly over each planet's annulus. Now, when I say annulus, I'm thinking about a ring where the planet is in the center, and halfway distance to the planets on each side would be considered the annulus, and he just took that material from each planet and spread it out in each annulus. And so you get an even distribution then of the material in our solar system, and that's called the minimum mass solar nebula. And that minimum mass solar nebula is shown as the red line there. It goes through, as you might expect, it goes through the terrestrial planets that are also plotted. And look, you get a really nice fit. You see a decrease in the density as you move away from the sun, which is exactly what we predict from a protoplanetary disk forming. As you move away from the sun, you should decrease in the density of the material, how much material you have. There is a problem in the asteroid belt. There is not enough material. I estimated where the bottom of the asteroid belt is. It might be lower, I don't know. The important point is that the asteroid belt is depleted in material. And we can explain that simply by remembering that a lot of material has been thrown out of the asteroid belt. As we've talked about in previous discussions, there are very unstable orbits inside the asteroid belt due to the gravitational pull of Jupiter and the Sun. And that's, of course, also why we haven't had a planet form in the asteroid belt. So we shouldn't be surprised that the asteroid belt is depleted in material. The same with the Kuiper belt. If you look out beyond Neptune, you see a drastic drop there in the red line when you get past Neptune. That's because the Kuiper belt has also been depleted in material. But the most notable thing is that we really jump in material when we hit this so-called snow line. Now, the snow line is this point in our solar system where as you move out from the sun, it's the point where water turns into ice. We call it the snow line for obvious reasons. So it jumps. And then you get the gaseous planets. And they do the same thing. If you spread them out along this minimum mass solar nebula, you get a nice declining line that's parallel to the one for the terrestrial planets. And again, it decreases in density as you go from Jupiter, inside of Jupiter's annulus, all the way out to Neptune. Beautiful in that respect. So this tells us, and we've known this for a long time, is that the solar winds probably carried in the early formation of our star, probably carried a lot of material out to the snow line and further on, thus enabling Jupiter and Saturn and the gaseous giants to become gaseous giants. If we look at just the rock and ice that's in their cores, we get this other line that is labeled rock and ice. And you can see Jupiter, Saturn, Uranus, and Neptune there. Still though, look, there's more material in that rocky center of the gaseous giants than we anticipated. So not only were gases like hydrogen and helium blown out there, but also terrestrial material was probably taken out there too, because that line is higher than the line we get for the terrestrial planets. So I hope that makes sense. Now, what we need to talk about, and it's another clever way, I think, to show this, is in this slide. Again, we're plotting the surface density in grams per centimeter square, and again, the distance from the sun in AU. And in this particular case, we have taken that extra material that we think was blown out into the outer solar system, and we've taken it and added it to the terrestrial planets. And look what happens when we do that. We get this beautiful fit. Venus and Earth and Jupiter, Saturn, Uranus, Neptune all fall along now the minimum solar mass nebula. So we have some problems. I've already talked about the problem in the asteroid belt. We know why that's depleted. The Kuiper belt, even if you add the Kuiper belt to Pluto in the area of Pluto is very depleted. Another reason why we don't use Pluto as a planet anymore. So we can explain those. The areas we can't explain very well are Mars and Mercury. they seem to be depleted. Now, we can surmise that Mercury probably lost some material to the Sun, and probably Mars lost some material to Jupiter, being gaseous giants. But we don't know. It's a mystery. That is the depletion in Mercury and Mars. But the cool thing is that there's a lot of evidence out there for the existence of this protoplanetary disk with an even distribution of material throughout it when the Sun first collapsed. So again, very cool stuff. Molecular cloud being forced to collapse by a supernova injecting it with all the right, lots of supernova, injecting new supernovae, injecting it with the right kinds of material, forcing it to collapse, forming a protoplanetary disk with even distribution. Now, the next step is how do we get planets from this protoplanetary disk, and it's going on right now in our solar system. So why not take a look at what we think happened 4.5 billion years ago or so when our solar system first collapsed. This is a picture of the rings of Saturn, and the moon that you see there is called Daphnis. And look at what's happening with that moon. It's actually looks like that black line is actually just empty space. It looks like the moon has formed from the material in the rings of Saturn. And if you blow up in the upper left there, if you blow up the area, you can see Daphnis is in the center, and you have nothing but space in between it. So this is a very good example of how you get maybe a planet, or at least a protoplanet, forming from a disk such as the one that we see out around Saturn. And we'll probably, through time, have more of those, so that eventually we'll lose the rings around Saturn. We call these things that form out of the protoplanetary disk, we call them oligarchs. You know, they're gonna scarf up material from the protoplanetary disk. Now, there's a problem with this. We know it happens because we can look at the rings of Saturn. We just don't know how it happens completely. The biggest mystery comes when we're trying to figure out how we get the particles to first come together, because they're not sticky, so we wouldn't imagine that they would naturally come together. Maybe it's a statistical problem. Maybe you get some concentrated in an area, and then they're enough to gravity will take over and bring some more into it, and it gets bigger and bigger that way. But how you start this process, we're not really sure. Maybe something comes in to that area and starts the whole process, kind of a seed, maybe some sort. I don't know. But once they're big enough to start pulling in other material, then you can start the process. And let me tell you how this happens. It's kind of cool. You form this mass. The oligarch is starting to form, and that oligarch starts to have gravity to it, and it starts to pull material in its surrounding area around this annulus that it's going to start scarfing up. And as that happens, the planet actually slows down from conservation of energy. I should say the oligarch actually slows down from conservation of energy. And wow, what happens then is, because it's slower than the material that's going around, more material hits it, it gets bigger, gets more gravity, pulls more material in, and then you've got runaway growth, basically, because the more material it picks up, the more it slows down, the more material it gets, until eventually it's scarfed up all the material inside its annulus. So you get then these various oligarchs forming as a result of this very, very cool process. A couple of points to make. Our solar system, as you know by now, is in a plane, and we would expect then the protoplanetary disk, of course, to be planar, and so all of these oligarchs are going to be in the plane of the solar system as they form, and eventually the planets that come from the oligarchs. That's one thing. They're going to be in very circular motion. When you have this conservation of energy, where the material is coming in to form the oligarch, that tends to make the material that's out there more elliptical, but forms the oligarch in a more circular orbit. So the oligarchs tend to be more circular when they go around the sun, and that's precisely what we have with the planets. I've already told you that the planets have slightly elliptical orbits, but they're very close to circular, and that can be explained by this process of conservation of energy, if you will. I just think this graph is to die for, because this is a computer modeling of what I've just been talking about. Well, let's first talk about that big red line on the right. That's to show a time sequence. You're looking at 5 graphs. We start out at 0 years in the computer model. We start out with a fairly evenly distributed amount of mass in the solar disk, and we slightly concentrated towards the left, and we are plotting AU on the bottom, that is distance from the sun. So we're going to be, in this particular model, going out to 1.6, which is roughly around Mars. And on the y-axis we have eccentricity being plotted. And eccentricity is real simple. It's the amount that a planet's orbit varies from a perfectly circular orbit. So if you have 0, you're perfectly circular. Anything greater than that, you get more and more elliptical. So eccentricity is a measure of that. And look what happens in the very first diagram where you start to form the oligarchs. The oligarchs are in black there. By the way, what's very interesting is you tend to form the oligarchs closer to the sun first. And look what's happening. The oligarchs are staying close to 0, nearly circular orbits. But the other material is being, whipped up and into these very elliptical orbits, which, by the way, makes them come back and crash into the oligarchs, which are slowed down. So another way that we can have this runaway growth. And as you go down, we can get, within about 400,000 years, we can get 12 or so oligarchs formed through this process. Fantastic. And then it takes another 100 million years or so. You can form the 12 oligarchs into about 4 planets. And as we'll find out later on, probably the Earth formed by its moon by a collision of a smaller oligarch about Mars size with Earth. But we'll cover that a little bit later on. I want to emphasize, though, that we still do have to deal with the gaseous planets. This is just modeling the interior planets. You can get pretty much the same result if you postulate that you're starting with an evenly distributed mass, but you add mass from the solar wind out to the snow line and add it to the gaseous planets. It's a little more complex, but that's what we think is happening. So I hope then that you're clear on the process of how we form the planets. We go from molecular cloud, we go to protoplanetary disk, we go to the formation of these oligarchs, and finally to the formation of the planets. It's a very beautiful operation. It takes Jupiter about 3 to 10 million years to form.